Thank you for joining us for this informative American Institute of Chemical Engineers webinar sponsored by Provenance Consulting, Introduction to Pressure Relief Systems. Our speaker is Justin Phillips. Justin Phillips has over 5 years of onshore and offshore oil and gas process engineering and project execution experience. His technical experience includes process design with specialty in flare and relief systems. Justin holds a BS in chemical engineering from Texas A&M University in College Station, Texas. He is a licensed professional engineer in the state of Texas. One quick note before I turn this session over to Justin Phillips. As described more fully on this slide, the American Institute of Chemical Engineers assumes no legal liability or responsibility for the use or misuse of the content in this webinar. And now I give you Justin Phillips. Welcome, Justin.
Thank you. Good morning and good afternoon to everybody. I'm sure it's the afternoon in most places of the United States right now, but it's still morning over on the West Coast. My name is Justin Phillips, and I'll be presenting today's topic, Introduction to Pressure Relief Systems. Before I start, I want to thank Pamela Benson, who just spoke, for her work in facilitating this webinar, and I also want to thank the American Institute of Chemical Engineers for allowing Provenance Consulting and myself to present today's topic. Pam, thank you for going over the ground rules. There is one additional point that I would like to stress to today's audience. Today's webinar is just the basics, and we will only be scratching the surface of something that I would consider a technically challenging subject matter. For some of you listening and watching, this presentation may open your eyes to pressure relief systems for the first time. You are my primary audience. For others among you, this presentation will help remind you of something maybe you learned a long time ago and maybe you've forgotten about it. You are my secondary audience. And for the rest of you, you may already be familiar with pressure relief systems, but maybe you're hoping to glean something new from today's presentation. Although I don't believe that you will get too much from today's content, we will have a question and answer session at the end, so hopefully I can address any questions that you may have. However, for this last audience, I do want to let you know that Provenance and AICHE are planning a follow-up webinar that covers some more advanced topics in pressure relieving systems, and we'll plan on having that a few months from now. So an overview. My goal for today's webinar is that all of you will walking away knowing what a pressure relief system does. Aside from that, I want you to understand what causes overpressure, what relief loads are, and which methods of relief are available to us. Lastly, I want to appeal to your intelligence and sensibility and try to convince you why you might consider working more closely with pressure relieving systems. And fair warning, this webinar is framed with the oil and gas industry in mind, but that doesn't mean that pressure relief systems don't exist elsewhere. They certainly do, as you'll see in the next couple of slides. So, what is the pressure relief system for? Well, what happens when you don't stop blowing air into a balloon? It eventually pops, right? Modern pressure relief systems came about over the last couple hundred years to keep steam boilers from exploding. As the world continued becoming industrialized, so did the prevalence of pressurized systems, and thus, so did the need to keep those systems from exploding. Honestly, a lot of things just don't blow up. Usually things just leak or crack open, which is still not a good thing. Pressure relief systems are, in a modern way of putting it, a way to prevent a loss of containment. But don't be fooled. A loss of containment is really just a pseudonym used in polite company. Loss of containment is not a good thing. It's very serious. So don't we have other things that prevent overpressure? Why would we need to have a dedicated pressure relief system if we have operators to control upsets? Well, the question is whether or not these things are always reliable. So for instance, why do we need a dedicated pressure relief system? We have motor switches to turn off pumps, or control valves to divert flow, or operators to bring a process upset back under control. Well, of course, these things can prevent an overpressure, but a well-trained operator can't always bring something under control if they're not fast enough. And a control system and a switch or a circuit breaker or some other gizmo is not always reliable. They will probably work, but that's the problem. They will probably work. Industry experience has shown that all of these things don't always stop an overpressure, so pressure relief systems have to stand up to the challenge. We could think about this in the Swiss cheese model, which you've probably seen before. Just imagine that the pressure relief system is the very last line on that Swiss cheese model. So where can you find a pressure relief system? The answer is almost anywhere. And even though you probably don't recognize them when you see them, I think that after we go through some of these examples, you'll start to see them everywhere. So the first example, and you can find this in many homes, is in a water heater. In your water heater, if it's kept in your attic or if it's kept in your garage, it has a pressure relief valve on it. You can find it under the hood of your car. A radiator cap is provided to keep things, if your cooling system in your car starts to experience too much heat coming into it, it can start to vaporize. That vaporized fluid will need to escape somehow, and it lifts up on your radiator cap and escapes through there. In your kitchen, you might have a pressure cooker. Pressure cookers have a weighted cap on the top to ensure that internal pressure never exceeds a certain threshold. Water, which is the component of interest in pressure cookers, will find a saturated equilibrium point above ambient conditions based on the cooker's cooking pressure. A clogged cap can lead to mechanical failure and a loss of containment of your pork and beans. Obviously, you can probably find a pressure relief system on an offshore platform. You can see the disposal portion of a pressure relief system in these photos of offshore production platforms. On the left-hand side, you can see a couple of flaring events. And on the right-hand side of the right-hand picture, you can see a flare boom. Flare booms and flare stacks are easy to spot, not just on offshore platforms, but also in refineries and chemical complexes. Sometimes they have a visible flame, which is a dead giveaway that they're a flare stack, but they'll always be far away from people and equipment. You'll find pressure relief systems in a shampoo factory. Like I said, you'll certainly find them in a petrochemical complex. Each of these pictures likely contains dozens, if not hundreds, of pressure relief system components, including valves, flare subheaders, and flare stacks. Those lucky ducks in the brewing industry require pressure relief systems too. During the fermentation process, yeast digests sugars, which converts them to ethanol and CO2. In a controlled enclosed fermenter system, the CO2 generation, along with an airlock, is used to maintain a slight positive pressure on the system, which keeps airborne contaminants out. However, a blocked airlock might cause an overpressure. So if you're driving around town, you might see a pressure relief system installed on your municipal water storage tank, a water tower, a standpipe, or just a tank that sits closer to the ground. Water towers and municipal storage tanks all have vents on the top of them. As the water column rises or falls during normal operation, there's an associated outbreathing and inbreathing of air to prevent over or underpressure of the tank. An imploded water tower is not easy to fix, and so that's why we have vents on them. And they're not just open holes. You can usually see them protruding from the tank themselves, so they might look a little funny. And there's usually a bug screen to keep things from crawling in and getting trapped. You can also find pressure relieving systems at school district's bus burn. School buses usually don't fill up with diesel at the Shell station, but instead, most school districts maintain their own diesel fuel storage for their fleets. Diesel fuel has the benefit of having a variable vapor pressure, which allows for storage at freely vented atmospheric conditions without the use of a gas blanketing system. So, in other words, it's easy to keep and maintain diesel fuel storage on site. These diesel tanks each have breathing vents on them to prevent over or under pressure during filling or draining activities. You can see them right along the middle of the tanks, pointing right up into the sky. And lastly, as a last example, this one should be pretty obvious, but humans, like any other living thing for that matter, has physical and chemical changes occurring constantly. When we eat, we tend to swallow a lot of air, too much air, and we burp it to get it back out. During digestion, our body may release gas into our intestinal tract to maintain homeostasis elsewhere. Swallowed air might make its way down the pipes. Bacteria in our gut feasts on sugar and expels gas, and chemical breakdown of food also releases gas. Our internal volumes can change dynamically, which is pretty neat, but there are physiological limitations. Too much pressure, not enough volume, and voila, our body relieves the pressure. So, who designs pressure relief systems? Well, I'd say that chemical engineers are uniquely qualified. So, for instance, some of the things that we study help us understand the phenomena which occurs. For instance, thermodynamics help us understand how fluids change with changes in enthalpy and entropy. Heat transfer helps us understand how fluids react to thermal changes and how fluids can affect their surroundings. Fluid dynamics help us understand pressure changes as a fluid moves from one place to another. And mass transfer helps us understand how fluid components move into and out of a phase and how relative component compositions vary across phases. These are just a few examples, but there are plenty of other courses that chemical engineers take during their formal education that are relatable to pressure relief systems. So far, we should all agree that pressure relief systems prevent or at least mitigate an overpressure, right? Okay, well, the next question is, what is an overpressure? Overpressure is exactly what it sounds like. It's an increased pressure that is higher than what is allowed. There's a corresponding term called underpressure, which is a decrease in pressure less than ambient. Think of it as a vacuum condition. Vacuum condition. So now let's talk about overpressure and what causes it. What could possibly cause overpressure? Let's say that you have a closed system. Imagine a sealed glass full of water, half full of water. So you could boil the water, that could cause an overpressure. You could pump more water into the system, which could cause an overpressure. You could add pure magnesium to the water and have a chemical reaction, or you could fill the container completely with water, no air bubbles, and then put it out into the sun. In that case, you might have thermal expansion. There's lots of stuff that could cause an overpressure. So one of the big questions is, how do we maintain consistency in industry when we consider the causes of overpressure? Luckily, over the years, the oil and gas industry has come to a consensus of what typically causes overpressure. API 521 has this standardized list of common overpressure scenarios, which ensures a certain degree of consistency for any overpressure analysis. So let's go through each of them and think of different examples that we might see in the facilities that we work in. Closed outlets. This is another way of saying blocked outlets. Let's say that you have a pump and you have a valve on the discharge of the pump. What happens if you close that valve? You can have a closed outlet. Inadvertent valve opening. Say that you have a high pressure system connected to a low pressure system with a valve that is always closed because the high pressure system would overpressure the low pressure system otherwise. What if somebody accidentally opens it? Failure of automatic controls. Let's assume that you have a high pressure vapor which is flowing downstream to a lower pressure system with a control valve. Normally the control valve would control the pressure to make sure nothing bad happens, but let's say it failed open. Maybe it'll cause an overpressure. You could have check valve failure. Check valves are a way of preventing flow from moving backwards back into a system from something else, but check valves are not always reliable. A check valve could get stuck open. You could have utility failure, which could lead to any number of things. For instance, you could have a loss of cooling. Let's say that you have a bunch of cooling exchangers which use water. If you have utility failure, specifically if you have loss of cooling water, maybe you've stopped condensing a fluid. If you stop condensing a fluid, you're not removing heat from the system, and perhaps that fluid, which is not condensing, stays a vapor, and it overpressures something downstream. Getting some strange animations on my side of this. However, I'll try to read it from what I can. We also have a loss of heating. We have reflux failure. We could have abnormal heat input. We could have an exchanger tube rupture. We could have transient pressure surges like a water hammer. We could have a fire. We could have process changes and chemical reaction, but there's even more than just this. So while API 521 offers plenty of help with pressurized systems, it's not entirely applicable to low pressure systems. If you remember a few slides back, we talked about diesel storage tanks and municipal water storage tanks. These are low pressure systems. API 2000 provides a standard list of common scenarios for low pressure systems. Going through a couple of them, we have liquid movement into or out of a tank. This is common with any tank. You have liquid coming in and you have liquid going out. So when liquid leaves, a tank will need to breathe in. When you have liquid coming, I can't remember which one I just said. When you have liquid leaving, you need to have breathing in. When you have liquid entering a tank, you need to have breathing out. You could have weather changes, which could affect the vapor space inside of a tank. So let's say that it's a nice hot day and suddenly a rain shower starts and the outside of your tank is cooled down very quickly and the inside gases that are there condense rather quickly. You're going to have an inbreathing event, and so you'll need a vent to prevent an underpressure. You could have a fire, which could cause boiling of the contents inside of the tank. You could have something called pressure transfer vapor breakthrough, which is a little complicated, but let's assume that you have a low pressure storage tank and you're transferring liquid into that tank using pressurized air somewhere else. So you're pressurizing air to push a liquid into the storage tank. Let's say that that liquid is now completely dumped into the storage tank, and now you're introducing high pressure air into your storage tank. You've got to have something to prevent an overpressure there. You could have a failure of pads and purges. Again, I'm getting a little bit strange animations on the slides that I'm seeing on the WebEx. I'm not sure if everybody else sees this. But you could have abnormal heat transfer due to a heat transfer device failure. So some storage tanks have what's called a lance heater to keep the inside fluid from freezing or from becoming waxy. Usually these turn on kind of like a thermostat. They reach a certain temperature, they turn on, they heat up your fluid, they reach another set point and they turn off. However, they are prone to failure sometimes, and it could stay on. If it stays on and it's too hot, you could start boiling your liquid and have a vapor that needs to be relieved. You could have a vent treatment system failure. You could have utility failure like we had previously. You could have a change in feed temperature. You could have chemical reactions. You could have liquid overfill. You could have a steam out condition. And if worst comes to worst, you could have an explosion or a deflagration. Or you might accidentally mix a different product in your tank. So the question is now, do all of these overpressures apply to any given piece of equipment or a system of equipment? The answer is of course not. Overpressure scenarios have to be qualified. So let's think of some examples. The first example is a water storage tank. It's very unlikely to be exposed to fire if there's nothing flammable around it, right? Another example is a valve. It's unlikely to be opened inadvertently if it is locked, closed, and other administrative controls ensure that operators never ever open it. Another example, you could have a centrifugal pump, which could be blocked in, but let's say that its pump curve falls short of causing an overpressure. So while you can block it in, that's not going to cause an overpressure. And another example, fire can occur around a vapor-filled vessel, but poor internal convection within the vessel may cause the vessel metal itself to fail before that vapor inside ever heats up, expands, and causes an overpressure. So we know about different scenarios, and we know that scenarios have to be qualified in order to apply. The question is now, how do you qualify a scenario? Sometimes overpressure scenarios are very apparent and readily qualified. But in my experience, in release systems design, two things are required to qualify any overpressure. One is process safety information, and the other is good engineering judgment. Process safety information, by the way, is also known as PSI, and it includes operating conditions, equipment design information, safe operating limits, piping and instrumentation diagrams, and related information. So what else helps qualify a scenario? 2 sets of eyes at least. This is true for a lot of different important things in life, and it's certainly true for relief system design. 2 sets of eyes will always be better than 1, because 2 independent minds will absolutely yield better judgment calls. So once we qualify an overpressure, we now have to think about how we quantify its relief load. So qualifying an overpressure is just one step in pressure relief system design. You can just say, well, fire is an applicable scenario, go order a relief device. You can't do that. Indeed, once we determine that a scenario can happen, we have to quantify what the relief load is. So the first example is possibly a fire. If we know the heat input from a fire, we can calculate how much vapor is generated from a liquid. Another example, if we know how big a failed open control valve is and what the upstream pressure conditions are, we can calculate what the flow rate is into the protected system. Another example, if we have a blocked-in centrifugal pump, we can determine a relief load from its pump curve. So we know we need to quantify relief loads, but how do we do that? Thankfully, again, we have some guidelines for how to quantify relief loads. So for the chemical engineers that are listening, if you think back to some of your introductory chemical engineering classes, you'll remember doing overall heat material balances. We set up boundary conditions, pressure relief, relief pressure, for instance. We add something to the system, maybe too much heat, and then we have to take something out of the system in order to get a balance. Relief loads can be from any number of empirical formulas, from theoretical relationships, from natural laws, or anything in between. It really just depends on the scenario. Sometimes it's tough, and sometimes it's easy. So far so good. We understand what causes overpressure. We understand that scenarios need to be qualified. We understand that relief loads need to be quantified. And the next question is, how do we stop an overpressure and how do we get rid of the relief load? Well, we can stop an overpressure with a pressure relief device, and we can get rid of a relief load with a disposal system. So, $1,000,000 question, what is a relief device? A pressure relief device is a system to relieve an overpressure in a controlled manner. It's typically a piece of equipment. Our pressure relief systems rely on pressure relief devices to relieve and stop overpressures. They usually come in many different shapes and sizes. Usually, when we think of pressure relief devices, we think of relief valves or PSVs. But there are also rupture discs, buckling pins, and other devices. Another thing to note is that pressure relief devices have lots of aliases and lots of acronyms. But they're known as PSVs, they're known as PRVs, they're known as SVs, RVs, so on and so forth. So the selection of a pressure relief device really depends on the application. Pressurized applications typically use relief valves. API Standard 520 Part 1 tells you the different types that you might consider pressurized systems. For low pressure applications, we usually use PVSVs, pressure vacuum safety valves, vacuum breakers, or open vents. So open vents themselves may not really qualify as a relief device because it's just an open vent, but the purpose is really the same thing. And a quick question, what if you don't have a vent on a low pressure system and you pull a vacuum? Well, a lot of people would say, it's not a big deal. Metal is pretty rigid, right? Well, right, metal is rigid, but it's also flexible. And I wish this animation worked, but it doesn't. Many of you may have seen this before. It's a tank rail car that is subject to a vacuum. And if you ever look it up, tank, rail car, vacuum, you will see this thing implode in a very violent manner. So even though metal is rigid, it's also flexible, and it's important to provide venting capacity to any sort of storage vessel. So a lot of people call a relief valve a PSV, which stands for pressure safety valve. So there is a difference between these two things. Safety implies compressible service. For instance, a pressure safety valve is used in gas service. Relief implies incompressible service. For instance, a pressure relief valve is used in liquid service. You can call them whatever you want as long as you and your audience agree with the intent and the meaning. As far as different types of relief devices, we generally have three: conventional unbalanced valves, conventional balanced valves, and pilot-operated valves, which come in two flavors themselves: modulating pilot-operated valves and pop-action pilot-operated valves. So reviewing the basic function of a pressure relief valve, this comes out of API Standard 520 Part 1. It's a cross-section of a conventional unbalanced valve. The protected system lies beneath. Let me grab my little arrow right here. The disposal system lies somewhere over here, off screen to the right. So the idea is that pressure reaches the valve set point and continues increasing into the realm of overpressure. The force against the spring right here causes the spring to compress and the disc, which is right there, to lift away from the seat. Valves are designed to achieve 100% lift within 10% overpressure. That is 10% above the set pressure for non-fire overpressure scenarios. For fire case, it's 21% overpressure, which happens to be 10% over 10% overpressure. The opening and closing characteristics of valves are important considerations during selection. A valve designed for vapor will behave differently than a valve designed for liquid if both were exposed to a liquid overpressure scenario. So as I mentioned, once our relief device relieves the overpressure, the relief load has to go somewhere, and a disposal system is where it goes. So there's generally three options for disposal, and we typically pick the safest, most cost-effective option. There are considerations that have to be made before choosing any of them. The first option is to save it. Typically, we'd only save predictable, small quantities of low volatility liquids or specialty chemicals. Or we could burn it. We typically burn anything that's gaseous, flammable, toxic, unsalvageable, uncontainable, or hazardous. In many facilities, we have to burn just about everything, but that doesn't mean we can burn it all together in the same disposal systems. Fluids may relieve at very different conditions than other fluids. For instance, one fluid may go into a disposal system at a very cold temperature, while another may go into the disposal system at warm, saturated conditions. If you mix those two relief loads together, you may get some phase change. You might even get ice formation, and nobody wants that, so segregated flare systems are not uncommon. The other option you have is to not burn it. You can send it to atmosphere. Anything that can discharge to atmosphere safely, steam, nitrogen, air, light hydrocarbons, in certain settings can just go to atmosphere. So moving on to the guidelines. We touched on guidelines previously when we mentioned API 521 and API 2000, but what are guidelines really? They are the rules of play. Yes, they can be confusing, and yes, they can be vague, and yes, they can be contradictory, though they shouldn't be. And trying to understand them and how to apply them may be difficult, but you have to start somewhere, right? We didn't understand how to read overnight, and we didn't understand algebra overnight either. So for the next couple of slides, I'm hoping that we can walk away with a good idea of how these guidelines relate to one another and how we can think about them. So what are the different types of guidelines? We have codes, which describe what you shall do. We have standards, which describe how you shall do something. We have practices, which tell us how we should do something. And then we have other things floating around like company standards, industry literature. So what about company standards? internal standards typically meet or exceed requirements of industry standards and practices. They also typically help us by telling us what a company's policy is for qualifying and quantifying an overpressure scenario and its associated relief loads. Industry literature may contain different problem-solving techniques or general reference material. Talking about code specifically, let's talk about codes. Which codes do we typically see that are related to pressure relief systems? Well, ASME Section 8 is probably the most common one. ASME Section 8 is a design code which specifies requirements for design, construction, inspection, marking, certification, and overpressure protection. Remember, codes tell us what we shall do. For instance, we shall provide overpressure protection. Here's some other common codes we might see. ASME Section 1, ASME Section 4, ASME Section 3, ASME Code for Pressure Piping B31, and then we get into another type of code. So aside from ASME's design codes, we have codes like OSHA 29, Code of Federal Regulation 1910.119. It isn't a design code like the ASME codes, and many people call it the Process Safety Management Standard, but it is a code. So what about industry standards? The most common with respect to pressure relief systems are API 521 Part 1, API 520 Part 1 and API 521. Remember, standards tell us not what, but how we shall do something. You shall provide overpressure protection by considering these scenarios and sizing relief device in this manner. Some of the standards, like API 650, are somewhat like codes of construction because they tell you how to design a tank, for instance. They're not technically codes, but they can be treated as such, so it's important to recognize them. So what do we have as far as industry practice? I think the most common one that most of us may be familiar with is API 520 Part 2. Practices are full of good advice of things that you should do. Practices may eventually grow into standards. API 520 Part 2 isn't just full of good advice, it's full of raggagaps, which are recognized and generally acceptable good engineering practice, which may carry certain legal significance. So now the next question I want to pose is, how could we fit all of these guidelines into an example workflow? The first thing you need to do is understand your needs. So let's pretend that we have a facility that falls under the PSM standard, and we have a new pressure vessel constructed in accordance with ASME Section 8. We know it needs to be protected, so we qualify and quantify with API 521. We size and select our relief device with API 520 Part 1, maybe even with a vendor catalog. Trying to get the animations to work, pardon me. We estimate piping pressure drops into and out of our relief device with API 521 and API 520 Part 2, and we iterate because we need the pressure drop can affect the flow rates, which can affect the pressure drop, which can affect our flow rates, so on and so forth. We keep iterating until we come to a convergence. So once we think our relief device is about right, we check the sizing of our disposal system with API 521 and iterate the pressure drop calculations, which again might mean iterating the sizing and selection. Eventually, you arrive at an answer and you check to make sure that your original needs are met. So moving on into a problem statement. In this example, I'm just going to go through kind of all of those steps to identify an overpressure, to quantify the relief rates, and then to size a relief device. So here's the problem statement. For some reason, if you can imagine this in your mind, you have a new liquid storage vessel that will be installed in your facility near some hydrocarbon storage vessels. It requires protection from overpressure. So what information do we know about this thing? It's designed to ASME Section 8. It has an MAWP of 50 psig. It's designed for full vacuum. It's oriented vertically, has a 5-foot diameter, 20-foot shell, has all of these different things. Maybe we should put this into a sketch. So the first thing to do is to qualify overpressures. There's a vessel. There's a pump it's connected to. There's an instrument air supply. And we note that it's nearby storage vessels full of gasoline. Sorry, I'm having trouble with this. Okay, so let's quickly identify what overpressure scenarios might apply. So the first thing we look at is perhaps a blocked outlet. If we have a blocked outlet, would we expect the pump to cause an overpressure? Well, the MAWP of our system is 50 psig, and the pump deadhead pressure we know is 37. Therefore, a blocked outlet on that pump would not cause an overpressure. Instrument air supply failure may. So the instrument air regulator that you see on the top left, if it fails open, it could expose our protected system to 120 psig air. There's an overpressure. We also note that it's near storage vessels full of gasoline. Gasoline is flammable. Let's say that there's a leak or loss of containment elsewhere, and that gasoline pools around our protected system, and there's a fire. Fire could certainly cause an overpressure. So how do we quantify those relief rates once we've qualified the overpressure scenarios? API Standard 521 provides some guidance. Let's start with the fire relief load. We calculate the fire relief load, W, from the heat input from fire, Q, and the latent heat of vaporization, L. You can find all of this fun stuff in API 521. So Q, the heat input, comes from an equation, C2, in this case, C2 is for inadequate firefighting capacity, F, an environmental factor, which depends on insulation, and area, which is the wetted surface area exposed to fire in our vessel. We get a Q, which is a heat input. We take our latent heat of vaporization at relief conditions. So once we find our latent heat of vaporization, we know our wetted area, and we know our heat input, we can calculate the relief load. W equals Q divided by L. So we have our heat input divided by our latent heat of vaporization, gives us a mass flow rate. The other relief load from the automatic control valve failure of the instrument air is calculated from control valve characteristics like CV and pressure differential across that control valve that's failed open. Typically, we assume that a valve will fail 100% open at the highest possible upstream pressure. So this is a 1-inch pressure regulator, and we would typically use the manufacturer's information for this specific make and model to get its control valve characteristics. For this valve, we found that its CV was 9.79, its C1 is 34, and its CG is 333. The differential pressure is the upstream pressure minus the downstream pressure. Our upstream supply pressure, we know a maximum is 120, and the downstream pressure is equal to our relief pressure. In this case, for a 50 psig MAWP vessel at, is this correct? Yes, it is. For 50 times 1.1, which is our allowable overpressure, if we take the difference, we get not sure what happened there. Oops. Anyhow, we'll eventually get our delta P. Sorry about that. Using the properties of air at the given conditions, along with an automated calculation, will yield quick results. And this result that I'm looking for is a mass flow rate through a control valve given certain characteristics like CV and delta P. The mass flow rate that we come up with is 3,103 pounds per hour. So now we know our two relief loads, and we know the size and select a relief device to meet the challenge. There are some equations that are supposed to show up, but they're not showing up in the slides that I'm seeing. which is a little unfortunate, but if we compare the two relief loads and we compare the two sizes that we need, we find that we would have to have an API-J orifice in this instance. I've got some notes. The area required for our fire case had a required area of 0.967 square inches, and the area required for automatic control valve failure of that air regulator was 0.563 square inches. So we have to choose a J in this case because it's 1.28 square inches, and an H would be too small, 0.75 square inches. So where would we install the relief device? We'd probably install it at the top of the vessel. Why? Well, if you install it at the top of the vessel, we want to have vapor being released this relief device. We don't want to have any liquid going through it. If we place a relief valve at the bottom or beneath liquid, then the first thing that's going to come out of that relief valve is liquid, and it has to come out of the relief valve at the same volumetric rate that the vapor would have to come out, which would increase the size required for that relief valve. So to make things easier, we install it typically at the top of a vessel. So once we have a good idea of the sizing selection of our pressure relief device, we estimate the piping pressure drop. We're not going to do the calculated pressure drop in this example problem, but I will point out a few guidelines and reminders. API 521 and 520 Part 2 provide some guidance. Inlet pressure drop must be less than 3% of set pressure. Outlet pressure drop cannot exceed the allowable overpressure for a conventional valve. 10% for the non-fire scenario, 16% if we had several PSVs, and 21% for a fire. Again, I'm having some issues with the animations on these slides. Let's go ahead and move on to the next slide. So sizing the disposal system. API standard 521 provides guidance here. So what should we do with our relief load? The contents of our vessel are non-toxic, non-flammable liquid that's similar to water. The other relief load is air. So both of these things are fairly safe. They're non-flammable, so we can vent atmosphere, but we need to do it safely. We would point the tailpipe from a relief device upwards away from personnel. So moving out of the example problem, onto the benefits of working in pressure relieving systems. I've got a bit of a bone to pick, and this is something that I picked up on when I first started working in the industry, and it pertains to certain attitudes towards relief system design, but I want you to hear me out. So in certain circles, when somebody says pressure relief systems, they groan about it like, I don't want to work on relief valves. Why is that? Is it because pressure relieving systems are conceptually and technically complicated? Really? You're a chemical engineer and you're worried about something being difficult? So what are the benefits of working in pressure relieving systems? One of the big benefits is that you will understand all sorts of processes. You'll understand how fluids behave. You'll understand unit operations. Again, having some issues on this, but you can maintain your mental acuity. You rely on a lot of things that you learned at school, including your fluid mechanics class. You do pressure drop calculations. Your thermodynamics class. You do changes in fluid behavior through nozzles. Your heat transfer class. You do thermal expansion due to continuous heating. Your mass transfer class. You're doing vapor-liquid equilibrium during upset conditions. One of the other good benefits about working with pressure relieving systems is that if you're thinking about becoming a PE or maintaining your license, pressure relieving systems is an engineer's paradise because the work associated with pressure relieving systems meets the engineering experience requirements required for PE licensure. So this brings us to the end of the presentation. Let's open up the Q&A. Pam, if you have any questions queued up, I'd like to take this time to try to answer as many as I could.
Okay, thanks so much, Justin. Let's see. Okay, my voice is being heard. So the first question, are burst disks acceptable as a PRD?
Yes, bursting disks, also known as rupture disks, are considered an acceptable pressure relieving device. However, there are certain considerations that have to be made before you choose one. One question you could consider, is it okay if your device opens up and does not reseal? So for instance, let's say that you have a process where you have valuable product that needs to be saved as much as possible. If you had an overpressure event and you had a rupture disk that opened and went to the flare, it would take a while before you'd be able to close that open path, and you may lose a lot of your valuable product to a flare system. So that's just possibly one consideration you can make for a rupture disk. But yes, generally, rupture disks are acceptable means of pressure relief.
Okay, thank you. Sometimes a PSV is required on a piece of equipment, but sometimes an upstream PSV can be sufficient. How do you determine whether or not a PSV is needed for equipment?
So there's a couple of things to consider here. One thing that I might look at is to see if there's any sort of intervening valves or intervening equipment between these two pieces of equipment, which each can have their own PSV. If there are no valves in between, and each valve in each piece of equipment has a PSV, perhaps one of those PSVs is not required. Something else that you may consider is that because of ASME Section 8 code requirements, your vessel, for instance, may require a PSV even though no other overpressure could possibly occur because, for instance, there's no possibility of fire, or the upstream PSV prevents the pressure from ever going into the system at or above the MAWP of the downstream system. However, because of ASME Section 8 code requirements, if you don't meet certain criteria and it is not documented correctly, you still must have a PSV.
Okay, thank you. What allowances must be made for potential solids in the discharging stream?
You definitely do not want solids in the discharge stream. Typically, in my experience, I don't have a lot of experience with solids getting into the discharge stream, except in the cases where you have very, very cold flow flowing into a wet flare header and causing ice formation. In those situations, it can be very dangerous because if you have the formation of solids inside of your disposal system, you're preventing the relief load from going to where it needs to go, which is the flare stack. If I was trying to fix a situation like that, I may consider segregating the flare headers, or I may find some other way of preventing the relief scenario from happening altogether. If solids are part of the process itself, for instance, there's a lot of dust, or solids just otherwise happen to be intrinsic to the process itself, you may want to use something like a rupture disc or something that can handle abrasive flow. Relief devices like pressure relief valves usually do not handle solids going through them very well.
Okay, thank you. If a valve is oversized, too large, is there any damage this may cause for a lesser relief scenario?
It's possible. So let's say that we have a conventional relief device which is way, way, way oversized for a very common scenario. Let's say that the relief device is, I don't know, an 8T10, which is a very large relief valve, and one particular scenario requires it to just be, I don't know, a 3J4 or something like that. It can be very problematic because you can, if it's in compressible service, for instance, you can open your relief device and you can have very high rate of flow going through that relief device. With that very high rate of flow, you may have excessive pressure drop, which can cause instability in the device.
Okay, thank you. What are the maintenance requirements for a pressure relief valve?
So pressure relief valve maintenance requirements may come from the code itself. They may tell you that you need to inspect in regular intervals to make sure that there is no damage, that the soft goods are in good repair, or you may have your own internal company standards which dictate how often you want to inspect, repair, and replace release devices. They are not devices. They're not things that you can leave alone and expect to work forever and ever. They are prone to wearing out. They are prone to breaking down, and so they need to be inspected.
Okay, thank you. How much credit can be taken for safety instrumented systems for overpressure protection?
That's a very good question, and so it sort of gets into the realm of from a pressure relief system point of view and a PHA or a HAZOP point of view. Typically, from the pressure relief system point of view, a safety instrumented system, so if you have a certain SIL rating, you may be able to take credit for that, eliminating the possibility or mitigating the possibility of a scenario ever occurring, and therefore reducing or I guess not having you, making it to where you are not required to consider that scenario as plausible. However, typically for automatic systems, we don't take any credit for them, but if there's a certain threshold of safety integrity level, then it may mitigate the possibility of the scenario completely.
Okay, thank you. Can you speak to pressure relief valve testing and inspection, frequency, in place versus removal, et cetera?
That is a complicated, that would be a rather complicated answer, and I don't know off the top of my head. However, if you repeat it one more time, that is a very good point. I want to consider it for the next webinar as something to talk about. Could you repeat it one more time, please, Pam?
Sure. Can you speak to pressure relief valve testing and inspection, frequency, in place versus removal, et cetera? Okay, ready for the next question?
Yep, go ahead.
What allowances must be made for potential solids in the discharging stream? Did we that one we answered already?
I think we may have covered that one already.
Okay, great. Okay, there's many more questions. For the two API standards, what is the pressure threshold between them? For example, what pressure does the 2000 standard go up to?
So that's fairly easy. For API 2000, it is designed for quote-unquote low pressure systems, and that's anything that is less than 15 psig. For API 520, Part 1, Part 2, and API 521, those are for quote-unquote pressurized systems, which are designed to operate above 15 psig all the way into the thousands and thousands of psig.
Okay, thank you. One of the slides shows C2 equals 34,500. What units are these in?
I can go back to that real quick. At least I think I can. I'm trying to get there quickly. Click, click, click. There it is. The question is about that equation. Q equals C2 times F times A to the 0.82. To tell you the truth, I don't know the units off the top of my head. If you look in API standard 521, if you look for the fire heat input equations, you may be able to find that. But I honestly do not know off the top of my head. I do know what the units of Q are and what the units of A are, but as far as the units of C2, it may just be a factor with some implied units.
Okay, thank you. Which one is better, choosing two regulators in series or installing a PSV?
This sounds like a question related to API 14C. And it is a bit of a tricky question. If you're going to ask me personally, I would think a PSV would be more reliable than two regulators in series because there's nothing to guarantee, even though it may fall into the range of double jeopardy, there's nothing to guarantee that those two regulators are going to act properly, one to close if something else happens or one to shut down a little bit more than it needs to in case the one that's upstream fails open. You can still have a failure, you can still have an overpressure because of those two, one of those two things failing. And in that case, you may still need a PSV or a vent.
Okay, thank you. Any experience in acoustic interaction in PRV inlet piping and how it relates to chatter as well as calculating acoustic line length?
that is a very hot topic of discussion within the API Standards Committee of Pressure Relieving Systems. There's a bit of material that is publicly available out there, but off the top of my head, I would not be able to speak intelligently to that question.
Okay, thank you. If I have a system pressurized with a centrifugal pump, known deadhead pressure less than vessel MAWP, is a PSV still required on the vessel?
It doesn't seem like it, at least not for the blocked pump outlet case. That was one of kind of the examples that I gave earlier about how to qualify an overpressure. If your pump at its absolute highest suction pressure and absolute highest, like at the deadhead position with the highest suction pressure, if you can't reach MAWP, then there's no overpressure.
Okay, thank you. Please speak to the process of marrying up PSVs into a flare system design. What standard and guidelines are there to assist in these calculations?
API 521 is usually the place that we go to talk about how we marry, for lack of a better word, PSV discharges into a disposal system. The exact calculations required to do all of those things are a bit left open to the user. There are certain tools available to users, commercial software like Aspen Flare System Analyzer, but the process itself is one that could be dictated by company policies, tells you which steps to follow and which things you need to iterate and which calculation methods or equations you need to use. I hope that answers the question, but it's typically a complex procedure.
Okay, thank you. What maintenance should we do on PSV and PSE?
I think we sort of talked about this earlier, especially with PSVs. With PSEs, which is a term that can imply rupture discs. For rupture discs, one of the maintenance items you may want to do is replace it every so often. You could also look to the manufacturer for any of their sort of maintenance activities that they think would be best suited for your application.
Thank you. Every day there are changes taking place in owner-operator facilities. How does an owner-operator stay apprised to these changes and how they are affecting the relief system?
The way to do that is with a very healthy management of change, or MOC system. A very healthy MOC system will help everybody involved with changes going on in the plant recognize when something is going to affect the pressure relief system of any given system.
Okay, thank you. Recently, a legal case permitted more than 3% drop on PSV inlet. Is this ever wise?
I don't know that the word permitted is accurate. This is also a pretty tricky point. The idea and what everybody feels safe about, nobody's going to argue that this is something bad to fall on, is to limit your inlet pressure drop to 3%. The reason for this is because of some reductive reasoning or reductive logic that has been formulated over the past several decades to minimize or eliminate chatter in a PSV. Limiting your inlet pressure drop does not always reduce or eliminate your PSV instability. However, that's what's written down, and that's what certain regulatory bodies will look at as a rule that you need to follow in order to prevent unstable operation and in order to fit within recognized and generally accepted good engineering practices. Nobody's going to argue that 3% is bad, but it gets sticky if it's more than 3%.
Okay, thank you, Justin. I'm sorry, but that's all the time we have for questions. So if your question was not answered today, please send it to producer@aiche.org. And now, on behalf of the American Institute of Chemical Engineers and all who attended today, I'd like to thank Justin Phillips for this very informative presentation. Thanks also to our participants for your cooperation and thoughtful questions. Please visit aiche.org to replay this webinar or to view and sign up for our many others. Goodbye, and we hope to see you again in a webinar soon.